So as I was saying about the way that stoichiometry problems are set up, first thing that we're going to do is we're going to read through it. We're going to look at it and see that it says how many grams of sodium metal are needed to react completely with 45.6 grams of water. So we see here, and we're going to check that our equation is first balanced. If you forget to balance the chemical equation, pretty much everything else is going to be wrong. So we're going to just double check, make sure that I have an equal number of atoms on each side. So I'm just checking, I'm seeing that I've got 2 sodiums on each side, I've got 4 hydrogens on each side, and looks like I also have 2 oxygens. Okay, so I've double checked that my equation has actually been balanced. So I know that I don't need to make any changes up there. And I'm going to start with my given value to start out with here. Always start your problems with your given value, just makes life easier for everybody. So then the first thing I'm going to do is I am going to look at the unit that I need to get to at the end. So I need to get to grams of sodium metal, starting with grams of water. All right, so first things first. We have to get from grams to moles. Now, why do we need to do this? Because grams are not great in terms of doing conversions. Moles are fantastic for completing conversions. So first thing I want to do is convert from grams to moles. So I'm going to set up an equation to do that. And where in the world did this number come from in the second portion of this? All right, where did this 18 grams come from? So to convert from grams to moles, we're going to use the molar mass of our compound. So this is a number that we got by going on the periodic table and adding the mass of hydrogen twice and the mass of oxygen once, and that gives us 18.01 grams. All right, so now the way that I'm going to set it up is I'm going to make sure that the unit of grams cancels out. So that's how you can tell in any one of these fractions what goes on the top and what goes on the bottom. So I'm going to double check, make sure, okay, my grams of water are going to cancel out here. And I'm going to circle the unit that's left. I'm now converted to moles of H2O or water, okay? So next step, now that I've gotten to moles, is I'm going to use that magical mole ratio. Remember, that's that magical bridge that we had. And remember that the mole ratio allows us to convert from one kind of mole to another kind of mole. So where do I build this mole ratio from? Well, remember, it comes from the coefficients that are in our balanced equation. So you can see why it's so important to balance our equation. So I'm going to pull from this here to build my mole ratio. And again, I'm going to double check that my units cancel out to make sure that I've written out my fraction correctly, which I have. So I'm going to now cancel out my moles, circle the unit that's left, and I've gotten to moles of sodium. So I'm getting closer. We've just got to get to grams of sodium. So now I'm going to kind of do the opposite of what I did earlier on. I'm going to use the molar mass this time to convert from moles back into grams. So that's where this number for sodium comes from. That's the molar mass of sodium. So I'm going to put that, because molar mass is grams out of 1 mole, and I'm going to make sure that I line everything up again by units, making sure that my mole portion of this cancels out. I'm going to circle the unit that's left and make sure that it matches up with the unit that I'm looking for. And because it does, we know that we have set up the problem correctly. Now, I know it looks like a lot of steps, but you notice that the units do most of the work for you if you are willing to write them out. That is the biggest mistake that students make with stoichiometry, is they try to skip writing out units, and it becomes very confusing very quickly. Just because something doesn't change radically from a mathematical standpoint doesn't mean we don't need to still set it up in this manner, because you need to have the full setup to make sure that you can write down the next step. So even, for instance, this mole ratio is a 2-to-2 ratio. All right, and I'm sure you're thinking, well, hey, it's a 2-to-2 ratio. It's not going to change anything mathematically. But what it does let you do is it helps you understand what you need to put for your next step. So that's why writing all of this stuff out, even if it's not going to change anything mathematically, is so important. So lesson 4.07 deals with limiting reactants. It's a slight twist of stoichiometry. Basically, with a limiting reactant, you have got one of your compounds that is being reacted with is going to run out before the other one is. And because one of them is going to run out too soon, basically what's going to happen is it's going to stop the reaction from occurring. So this can be obviously pretty, difficult to deal with if you have a limiting reactant, because you're not going to get what you thought you were going to get. You can only get out of a reaction as much as the limiting reactant will give you. So remember that limiting reactants are used up first. Your excess reactant is the difference between your theoretical yield and your actual yield. It's your leftover, or it's the stuff you're not going to get to use as a result of the limiting reactant being there in the first place. So think of them as leftovers. So the basics behind this mathematically is not too different from a stoichiometry problem. It's just you're going to make two of them this time. So the other big thing with limiting reactant problems is you're going to see two pieces of information to start out with, all right, and two different types of compounds. And that's a dead giveaway that you have a limiting reactant problem. As soon as you see that, hey, I've got to, build a limiting reactant problem. But it's the basics behind this again. You are going to be balancing your chemical equation. You'll check to make sure that it's balanced. And this time around, we're still going to start with our given amount, except that we have two of them. So like I said, we're going to build two stoichiometry problems instead of just one. So you can see the basics behind this. It's stoichiometry. It's just there's two of them instead of one. That's really the biggest difference. So again, what are we going to do here? We're going to use our mole ratio to do our conversion here. And remember, that comes from our coefficients. And again, I know what you're thinking. It's 1-to-1 ratio, but remember, it shows you whether you have something set up properly, and it shows you what your overall yield is going to be. Now, the answer that ends up being the biggest one is going to be your theoretical yield. That's what, under perfect circumstances, what you could theoretically get. All right, this is if like everything was to go right that day. Your actual yield is what is actually going to be produced, what you're actually going to get on that day. And the thing that shows you the actual yield is also going to be your limiting reactant. So basically, HF or hydronium fluoride is going to become our limiting reactant. Now, dealing with those two terms of actual yield and theoretical yield, all right, we have one final twist in Module 4, which is percent yield. All right, and percent yield is actually a pretty basic equation. It is actual yield divided by theoretical yield times 100. So the basic steps for calculating percent yield are to write out the balanced equation for the reaction. So we've heard that and seen that now quite a bit. So we want to make sure that that is pretty much the first thing that we always check for and do. Second thing that we're going to do is we're going to identify all important information provided in the word problems or data table. We're going to solve for the theoretical yield of the reaction. And basically, again, we're going to be using stoichiometry to do it. Finally, we're going to divide the actual yield by the theoretical yield and multiply by 100 to get our percent yield. So this is an example of what one of these looks like. Following all of these steps, again, checking to make sure that the equation is balanced, going through stoichiometry, in this case, we're starting with grams of magnesium, and we're trying to get 2 grams of magnesium chloride. So again, this is all stoichiometry. It's all stuff you've seen before. Here's the twist at the end. That last final step, we're going to take our actual yield, all right, put it on top, take our theoretical yield, put it on the bottom, multiply it by 100, and that's going to give our percent yield. So those are the basics behind these, and I hope you enjoyed this review. I hope it helps you out on your DBA.